Hi guys, today we're going to talk about upgradable smart contract. In traditional smart contract, once you deployed it, it cannot be changed or updated. However, with upgradable smart contract, it gives the mechanism for developers to basically change the contract logic and functionality without affecting the state and the data. A few reasons why we need to basically change or update a smart contract is because we need to fix bugs. Second is to enhance security, or third is to implement some other functionalities that we want to incorporate in our smart contract. So without further ado, then let's go start and create our upgradable smart contract. For this tutorial, we're going to use Wix IDE. Just go to this URL right here in order for you to use Wix IDE. For this tutorial, we're going to be creating an upgradable smart contract. So first, let me explain to you what would be the structure of our smart contracts. In this session, for the upgradable smart contract, we will have 4 smart contracts that we are going to deploy in the network. The first one is the my contract. That's all. Basically, this contains the implementation logic for our application. The second one is the my contract underscore v2. That's all. This is also where the implementation logic resides. However, this is the upgraded version. So once we upgrade our smart contract, this smart contract will be the one we are upgrading in. So the next smart contract that we're going to create is called proxy.sol. Basically, this will be our main smart contract. So for example, if you're creating a decentralized application, then the proxy.sol will be the main contract the users are interacting. And then the proxy.sol will handle all of the delegate call to a implementation contract, which is right here. The last contract, the fourth contract that we are going to create is called proxyable.sol. So this proxyable.sol smart contract makes our implementation contract upgradable via proxy. So now we'll start writing our smart contracts. And the first smart contract that we are going to write is this proxyable.sol. Since this proxyable.sol will be imported by our implementation logic smart contracts right here. So we will be writing this one first. So in our file explorer, just click this create new file button and name our new file proxyable.sol. In this it will open a new text editor pane where we can write our smart contract codes. And the first one we're going to write is basically to identify the license that we are going to use for this smart contract, which will be MIT. Next is we need to specify the version of Solidity that we're going to use for this code, which is 0.8, which is 0.8.0. Next is we will define the smart contract now, and we just need to write contract followed by the smart contract name, which is proxyable, and then the curly braces right here. Now inside of the proxyable contract, we write the function. The name of the function will be update code address, and the parameter will be an address type with the name of new address. And we need to make sure that this particular function is entered out. So inside of this code, we will have a require statement, which will I paste right here. So now that we have the require statement right here, we'll paste another set of code. This one is the assembly code. So later we'll explain what this function does. So we will need to create another function for this smart contract. And this particular function will have a name proxyable UUID. And this proxyable UUID will not take any parameter. However, it will be public, pure, and it will return as a byte 32 data type. It will return as a bytes 32 data type. And inside of this function, we'll just paste this return statement right here. Basically, this is what the contract proxyable contains right here. So now let's explain what is happening inside of this smart contract. So you might be wondering where this hex string came from? It came from this. So passing the word proxiable or caps in a CACAC 256 hashing function will basically return us this hex string. And this is the hex string that we'll use as a reference to the we'll use this hex string to reference the storage slot in the blockchain network. So for the function update code address, it takes a parameter of address named as uAddress, and then inside of it, we have a require statement right here. Basically, what it says is that this hex string must be equals to the hex string that is returned by our proxiable UUID function, which is right here. And since it returns the same hex string, then it means that our code will push through to the next line, which is this one. And this one states basically that we are trying to insert an assembly code. And inside of that assembly code, we call the ss_store function and pass in our hex string as a reference to the particular slot in the blockchain that we want to save our new address, which we passed here in the update code address function. So basically, that's how this smart contract proxiable works. So now that we're done writing the proxiable.sol smart contract, we can now proceed in writing our next smart contract. Just create another file and then name this my contract.sol right here, and then specify the license and the Solidity version that we're going to use, which is 0.8.0 and above. Next, this smart contract will import the proxiable smart contract that we have created earlier, right there. And now we'll basically create the contract using the contract keyword. The name of our smart contract would be my contract. And we will extend the proxiable smart contract right here. So inside of this smart contract, we have 3 state variables. The first one is the address of the owner. And the second one is a unsigned integer count. The third one is a boolean. It's public, and the name is initialized, which is equals to false. Next, we're going to write a function called initialize, and it doesn't have any parameters, and the code inside of it basically. And inside of that function, first we have a require statement right here, which checks if the owner is equals to the address 0. And if it is, it will be the transaction. If it is, then the transaction will be reverted with a message that says already initialized right there. Next, we have another require statement that checks whether the smart contract is already initialized or not. And if it is initialized, then we pass a message that says already initialized. That's right. After these 2 require statement, we then assign the owner to be the message that sender and the initialized to be true. And let's make sure that this initialize function is set to public. So what this initialize function does is that this will act like the constructor in this smart contract. So when this function is called, it will be called via our main contract or the proxy contract. And this will be the one which will be initialized, setting the owner to be the message that sender and initializing this smart contract to be true, which means that the smart contract that the proxy contract is delegating its function calls will be directed to this smart contract. The next function that we are going to discuss is the function. The next function that we are going to discuss is the function called increment. It doesn't have any parameters, and inside of this code, we just add 1 to the existing count variable. And let's just make sure that this function is also public. The next function defined inside of our smart contract would be the function. The next function defined inside of our smart contract would be the function called update code. And it takes a parameter of an address type, new code. And inside of this particular function, we call the update code address and passing in the new code as its argument. We make sure that this function is executed only by the owner and it should be public. This particular code actually exists inside of our proxiable.sol. So if we check proxiable.sol, you can see that this is the function that we are basically calling. And since we inherited proxiable.sol, then we can definitely call this function right here. The next one is we just need to define the modifier only owner, since we have this particular modifier here in this update code function. So inside of this only owner modifier, we have a require statement that checks whether the message that's rendered is equals to the owner. And if not, then we can say that only owner is allowed to perform this action right there. And we just pass in the underscore right here, which means that execute the following code after the call to the only owner modifier. Now we are done with our second smart contract and we'll now proceed to our third smart contract. So again, in the File Explorer, just create a new file and then name this file proxy.sol. And of course, we add the license identifier and the Solidity version that we are going to 0.8.0. And then after that, we define the contract. And the name of the smart contract would be proxy. As simple as that. And then inside of this proxy smart contract, we will have the constructor. And it will accept two parameters. The first parameter is a bytes type, memory, construct, data. And then the second one is an address type also, which is the contract logic. So inside of this constructor, we will have an assembly code right here. And inside of that assembly code, we will just call this SS store function that I will paste right here, right there. And remember that this particular hex string is equals to the proxiable word that is passed to the KECAC 256 hashing prompt. So let me put that here. So basically, let me put that. Okay. Now after this call to the assembly function, basically what the assembly function does is it stores our contract logic, which is the address of our implementation contract, which is equals to this my contract.sol. So my contract is our implementation contract, which is also called the contract logic inside of our proxy.sol right there. So after this assembly code, we will now delegate a call to the contract logic. So to do that, we just type contract logic.delegate call, and passing into the delegate call is the construct data that we passed here as a parameter to our constructor. And of course, we need to capture whatever this function will return to a boolean called success right there. And then after that line, we have a require statement which check whether the delegate call is successful or not. Then if it's not successful, we will revert the transaction with the message of construction failed. Construction failed. Next is we will have a fallback function, which is an external and payable function. To give you an idea of what a fallback function do is that every time we call a function, or every time, to give you an idea of what the fallback function does is every time we access the proxy smart contract, then the fallback function is executed. So whatever is inside of this fallback function will be executed every time we access the proxy smart contract. So inside of the fallback function, we have an assembly code. So inside of that assembly code, we have this first line, we basically create a new variable called contract logic, and we load whatever data is inside of this particular hex string. So that particular hex string or that particular slot stores the contract logic or the implementation smart contract address. The next line after this is a call data copy, which basically copies all of the call data that we execute in this smart contract. The next line is the call data copy right here, which basically copies all of the call data we executed when calling this particular smart contract. The third line is a delegate call, which basically it computes for the gas, and this particular delegate call is calling the contract logic, which we defined here. And we pass in the call data size of it, and we assign whatever this function returns to the variable success. So the next line is this one. It just basically returns the data size of the delegate call right here. And then it is followed by this line, which basically copies the return construct. This next line basically copies the return data that delegate call returned. And then the last few lines is a switch statement right there, which check whether the delegate call right here is successful. So if it's not successful, then it will be handled by case 0, which means that the code that will be executed will be a revert transaction. And if this particular delegate call succeeds, then we will just return whatever the data size is. So now this is what our proxy smart contract do. Basically, our proxy smart contract is, as I said earlier, the main contract that we are going to interact with in our decentralized application or whatever decentralized application you are using. So now, the last smart contract that we're going to create is just a copy of the my contract.sol right here. So what I would do is I'll just make a copy of it and paste it inside of here. And I will just rename the file to mycontract_v2.sol. And inside of the smart contract code, I'll just change the name to mycontract_v2 to designate that this is the second version of this particular smart contract. So the only difference that we will have in this smart contract is that we'll add another function right here. We'll just copy the increment function right here and then change the name to decrement, which will basically lessen the count by 1. So this is the only difference of my contract v2 to the my contract smart contract. So what this version 2 of the my contract does is that this will be the smart contract that we are going to upgrade into. So for example, this my contract.sol basically doesn't implement the decrement function. It only implements the increment function. So for example, in the future, what if our users want to have a decrement function? So this is where the concept of upgradable smart contract comes in. So this is where the concept of upgradable smart contract comes into play. So basically, what we can do is we will deploy another smart contract which has the decrement functionality right here, and then we will update our smart contract via the proxy.sol or the proxy smart contract. And after that particular update, we will now have the mycontract.su. After that particular update, we will now have mycontract v2 smart contract as our implementation contract. Now we are done with the writing of our smart contract, and we can now deploy this smart contract, these 4 smart contracts. Okay, so now we are done with the deployment of the three other smart contracts: proxyable, that's all, my contract, that's all, and my contract v2, that's all. Now we're going to deploy our proxy smart contract right here. And for this one, upon deployment, we have two constructor parameters right here. So we need to supply those particular parameters before we deploy our smart contract. And right here in the deploy section, we can just press this arrow, and the two parameters the constructor is asking is the construct data and the contract logic. So for the contract logic, it's quite simple. It's just the address of the implementation logic smart contract, which in this case is the my contract. That's all. So I have copied the deployed address right here. So I'll just copy it and paste it right here. Now for the construct data, this one is a little bit more complicated since remember that in our my contract, that's all, basically this function will act as our constructor for this particular smart contract. But in order for us to access this particular function via our proxy, that's all, we need to supply the construct data of that, or the call data of that particular function inside of our my contract, that's all. And in order for us to do that, we can just go here in the Remix console right here, and we can just type web3.utils.sha3, and inside of it pass the word initialize, parentheses, like this one. So basically this is the same as the name of the function right here. And then after that, we add a method called substring, because we only need to have the first 10 strings of this particular hash, and press enter, and it will return this particular hex string right here. So what we can do is just copy this string, and then in the proxy.sol deployment, just paste that particular string right there, and then also paste the smart contract logic implementation address right here. And once that is done, we can now click transact to deploy this particular proxy smart contract. Compare. Okay, so now we have successfully deployed all four of our smart contracts that we are going to use for this video tutorial. Now, in your local machine, create a file called index.html, and then paste the HTML code right here. So this is the entirety of our front-end code right here, and we can see what it looks like by using an extension called Vibe Server right here. Please install this extension, and then you can go to our file explorer, right-click the index.html, and then select Open with Live Server right here. And it will automatically set that the server has started at port 5500. And in order for us to access that particular port or website, we can just open our browser and then type localhost 55,000 right here, and it will open this this website for us. Okay, currently this website won't work since we don't have the contract address indicated here and the ABI right here. So before we proceed in putting these values right here, we can just discuss a bit about the structure of our HTML. So inside of our HTML, we will render a button, and that button will connect our wallet to this particular website. And then if it's connected, then we will be rendering the setup buttons and an input box. So this button has functions called increment, decrement, and to get the current value of the count variable, and this part is where you update your code. So at the bottom right here, we have the script tag, and this is where all of the JavaScript resides inside of our HTML file. So what we do here is we first define so what we do here first is get the element that has an ID of after connect, and we hide it first. And then we initialize the account and the contract to null. And then inside of this connect function, this is an asynchronous function. So if there is a wallet that is trying to connect to this website, then it will practically connect that wallet to this particular website. And also it just renders some additional elements in our HTML code right here. And then these other functions, increment, basically what it does is it calls the increment function that is written inside of our implementation contract, which is the my contract, smart contract, or my contract, that's all. The decrement function also does that. Instead of calling the increment function inside of our smart contract, it calls for the decrement function. Now this function, current, basically it gets the current value of the count state variable inside of our function, or inside of our smart contract. The last function right here is this update code. And what it does is basically it gets the contract address value that is inputted inside of our input box, which is right here. So if we put a valid smart contract there, then we can change our smart contract later on. And then once we get that value, we basically call the update code function right here on our smart contract. And then we just erase, or then we just remove the values inside of the input box after this call to the particular function. And then we log that we are successfully connected to that new contract address. So now we can change the value of the address variable right here, rather insert the value. So we can go back to our Remix IDE and go to the proxy.sol, since we listed the smart contract address of this particular file right here. So we will just copy this and paste it inside of here. So why do we need to get the smart contract address of the proxy instead of the my contract.sol? That is because the proxy smart contract, this one, will be our main contract that we interact to. And then every time we interact with it, there's a fallback function that sends all of the call data to our my contract.sol. So every time we interact, it basically delegates the call to the contract.sol right here. Then as for the value of the API, what we need is the API for our implementation logic right here, which is the my contract.sol. So in order for us to get the API, we can go to this compilation tab and then just click this copy API to clipboard. And it will automatically copy the API right there. Just delete this square bracket and then paste the API right here. So now we basically have the API. And now this website should now be working properly. So now we can go to the website that we have launched earlier, and then right here, press the connect button so that we can connect our MetaMask wallet to this particular website. MetaMask will pop up saying which account you want to connect to. Click next and then just click connect. So now we have the increment, decrement, get value button, and then the update button. So this time we'll just increment. So this time we'll just press the increment button. And MetaMask will pop up saying that it wants to increment, or you are interacting with the increment function. And just click confirm. And let's wait for a while for the transaction to finish. And once it's finished, basically you can see here that the current value has changed from 0 to 1. So now let's increment again. There, so after the transaction is done, you can see that the current value will change to 2. So you notice there is a decrement button here. So every time we press the decrement button, it gives us a type error like here, saying that the decrement is not a function. This is because in our my contract, smart contract, our first implementation doesn't have the decrement function right here. It only has the increment function. And also in the API that we pasted right here, it doesn't contain the decrement function. So basically, that's why it will give us an error like that one. Okay, so now let's say that you want to implement the decrement functionality for this particular website or for this particular decentralized application. So how would you be able to do that with the upgradable smart contract? So what you can do actually is just pass the new contract address of the implementation logic or the new version of the implementation smart contract, which in this case is the my contract v2.sol. And this is the contract address. You can just copy it and then paste it right here. And once we click update, MetaMask will pop up saying that it is calling the update code function inside. Just click confirm. And then let's wait for the transaction to finish. So once the transaction is finished, you can see here in the console that successfully logged the value or the smart contract address of our new implementation contract, which is the version 2. But right now, it still won't work. Why? It's because we still don't have the decrement function inside of the ABI we have right here. So we have right here. So what we can do is go back to remit right here. And in the my contract v2.sol file, compile this particular smart contract, and then let's copy the ABI of this particular smart contract. Let's go back to index.html, and then we can just select the entire ABI, delete it, and paste the new ABI right here. Now, we can now execute the decrement function right here, and it won't give us any error. So first, connect the wallet. First, let's check the increment function. So let's click increment, and here confirm. And there, you can see that the current value is increased by 1 again using the increment function. Now, let's call the decrement function or the decrement button. And you can see here, click confirm. And now you can see that the current value is now decremented by another value 1. So that is how we basically implement an upgradable smart contract. So again, to give you a high-level overview of what's happening here, basically the proxy contract or the proxy.sol right here, this one handles all of the transaction that is happening in your decentralized application or your smart contract. This is the main smart contract you interact with. And every time you interact with this particular smart contract, it basically calls this fallback function and executes everything inside of it. And what this assembly code does is it basically delegates all of the call from this smart contract, proxy smart contract, to the implementation smart contract, which is this one, the my contract. Which is this one, the my contract, that's all. So just a few reminders, when you are creating a new version of your smart contract that you want to upgrade, please make sure that the state variables right here are in the same order as you previously defined in your my contract, that's all. The reason here is because every particular state variable is assigned a particular slot in the blockchain network. So for example, this address public owner will be in slot 1, and this count variable will be in slot 2, and this third variable initialize will be in slot 3. So if you decided to upgrade this smart contract, maintain this order. Otherwise, if you change the order, then there will be a problem accessing these state variables inside of the blockchain network. For example, in our my contract 2.sol, we basically change the order. Then it means that the count will change to slot 1, the initialized will change to slot 2, and the owner will change to slot 3. And whenever you are accessing the count variable right here, it will basically give you the previous slot 1, which is an address type. And uint is not equal to an address type, so there will be an error inside of your code or your smart contract whenever you are doing that. So let's undo the changes we have made here and retain this particular order. So another reminder here is that the proxy smart contract, it handles all of the state variables that we have in our smart implementation smart contract. So basically, all of the states are stored in the proxy smart contract. So whenever you check the states of your implementation contract, basically it won't change. And everything is handled by the proxy smart contract. So that when you upgrade to another version of your implementation contract, for example, you upgrade, and then you implement the implementation contract version 2, the original or the previous state of the proxy smart contract won't change when you upgrade to the implementation smart contract. So basically that's how proxy smart contract works. So they store the state and then delegates all of the function call to the implementation smart contract. So here in Polygon Scan, the Mumbai Polygon Scan, we can paste the smart contract address of our proxy.sol, and then let's find it. And you can see here the transactions that we have made inside of this smart contract. Now let's check the smart contract for our first version of our implementation contract, which is our my contract.sol. So let's paste the address right here, and you can see that the only transaction here is our contract creation. Also, when we check the version 2, right here, copy our smart contract code and paste it here. You can also see that the only transaction here is the contract creation. So now back in Remix, what we can do is load our mycontract.sol and paste it here. And once we check the count, it will return as 0. So after we check the count, it returns as 0, which means that the count variable right here wasn't incremented or decremented at all in the mycontract.sol. And it should be the same with the version 2 of the mycontract. That is because back here in our whiteboard, as I've said earlier, the state is handled by our proxy smart contract. So that is why whenever you check the count in your implementation contract right here, the version 1 or the version 2, it will return, both of it will return 0. So that is how proxy smart contract and upgradable smart contract work. So this is basically the end of our video tutorial right here. So I hope you guys have learned a lot from this particular tutorial. And thank you, and I'll see you again on the next video.